this lecture I am going to discuss the electromagnetic waves in vacuum. Now we look at wave equations for E and B. In a free space, the charge density is 0 and current density is 0. So the Maxwell's equations are divergence of E is equal to 0, divergence of B is equal to 0, del cross E is equal to minus dou B by dou T, and del cross B is equal to mu naught epsilon times dou E by dou T. So these four equations are partial differential equations, first order coupled partial differential equations. So we can decouple this by applying curl on, let's say, Faraday's law and Ampere's law. So first we apply curl on both sides on Faraday's law. So del cross E bar is equal to minus dou by dou T of del cross B bar. So this further we can write it as gradient of divergence E minus del square E is equal to minus dou by dou T of mu naught epsilon times dou E by dou T. So we know that divergence of E is 0, so simply we have minus del square E is equal to minus mu naught epsilon times, so dou square E by dou T square. So this minus they get cancelled. So we get, what is this called? This is a wave equation for an electric field. So similarly we apply this curl to Ampere's law. So this is del cross B is equal to mu naught epsilon times dou E by dou T, and when we apply curl we see what happens. So del cross B mu naught epsilon dou by dou T del cross E. So this further we can write gradient of divergence B minus del square B, and we know from Faraday's law what is del cross E, which is minus dou by dou B by dou T. So we get del square B is equal to mu naught epsilon dou square B by dou T square. So this is a wave equation for magnetic field. So let's call this equation 2 and this one as equation 1, and we say that the solutions of 1 and 2 would be a traveling waves. So E is equal to E0 e power I k dot r minus omega t, B equal to B0 e power I k dot r minus omega t. Here E0 and B0 are the complex electric and magnetic fields. So these two should satisfy equation 1 and 2. So by substituting the solutions back in equation 1 and 2 should satisfy the equation. So let's take equation 1 and substitute this. So del square is equal to a mu naught epsilon times dou E by dou T. So when we differentiate the wave function, complex wave function, so we get I times k. When we do dou by dou T, then we get minus I omega. So when we differentiate this, as we are doing it twice, so this will be I times k whole square, and we end up E0 exponential of k dot r minus omega t. Similarly, we substitute here mu naught epsilon, where dou square E by dou T square, which means for one dou by dou T you get minus I omega. So we get minus I omega square, and then E0 exponential of k dot r minus omega t. We see this and this, they are common, and so what do we get here? We get, so I k whole square is equal to mu naught epsilon times minus I omega square. So where we know omega is equal to k into v, where v is the speed of the wave and omega is the angular frequency. So k square is equal to mu naught epsilon times omega square mu naught epsilon k square v square. So v is equal to under root of mu naught epsilon, where mu naught is permeability and epsilon naught is permittivity. So this constant mu naught and epsilon naughts are the constants in a Coulomb's law and Biot-Savart's law. So when we substitute these values back in this, so we end up V is equal to C. So and we go back and rewrite equation for E and equation for B. So the equation for E is del square E is equal to 1 by V square dou square E by dou T square. What is this? This is a wave equation for E in a medium, and if it is in free space, then it would be del square E is equal to 1 by C square dou square E by dou T square. This is a wave equation for E in vacuum. So now uh, we say that in free space EM waves travels at a speed of light, or free space supports the propagation of electromagnetic waves at a speed of light. Now all this we are seeing because the Maxwell added a term to the Ampere's law. Had Maxwell not added these extra terms to Ampere's law, we would not have seen a wave equation, and we would not have studied this electromagnetic waves at all. So it is so important in a electromagnetic waves. The contributions of Maxwell's to Ampere's law is very important. What is that? The mu naught epsilon times dou by dou t, dou E by dou t is the term the Maxwell added to Ampere's law. So, and because of this we see or obtain a wave equation, and subsequently we studied electromagnetic waves. Okay. Now let's suppose that the wave direction k bar is k times z cap, which means now we fix the direction of wave propagation, and the position vector is xi cap yj cap plus zk cap. Then k dot r bar is simply kz. What is k dot r? Which is oscillations in space. And what is omega dot t? Omega t, which is oscillations in time. Now let's suppose that this is a k vector which is propagating like this. The projection of k onto x is k x, and this is ky. Now we draw a line which is perpendicular to k. So this is a line which is perpendicular to k. Now there is a position vector which is making an angle theta with respect to k. So this is a theta. What is this blue line? Is the position vector, and what is this black line is k vector, and what is angle between them? Theta. So k dot r, now the projection of k onto r is r onto k is r cos theta. So what is this? This is now this value is r cos theta. So simply k dot r is k r cos theta. R cos theta is the component of r along k. Now k dot r cos theta is the value which is constant, is a constant on a line on the line drawn perpendicular to so this k dot r cos theta is constant over this red line. Okay. Now we draw another line at the center parallel to perpendicular to k. So this is so these two, basically these two lines are parallel to each other. Which one? The red lines are parallel to each other. So here k dot r is 0. In this case k dot r is 2 pi. So which means that the two lines are separated by lambda. Okay. So on the red lines the field is constant. The field is uniform. Field is uniform. So we say now that the k dot r is constant on the lines drawn perpendicular to it. So what are the plane waves? Waves traveling along one particular direction has no dependence on other two directions. So let's say this is a plane. The field is uniform over this plane, and the field, what happens? The field is uniform here, and what is the direction of propagation? In this direction. So a field is uniform over a plane perpendicular to the direction of wave propagation is called a plane wave. Okay. So we can write this as E is equal to E0 exponential of kz minus omega t. So this is a plane wave which is propagating along z axis, has no dependence on x and y. So therefore we say this is a plane wave. Similarly we can write for B also, which is B0 times e power I kz minus omega t, where E0 and B0 are the complex amplitudes. So what are these two waves? They are the plane waves. Now a monochromatic wave, a wave of single frequency, is called a monochromatic wave. So now we look at the Maxwell's equations. The Maxwell's equations impose extra constraint on E0 and B0 on amplitudes. Since divergence of E bar is 0 and divergence of B bar is 0, we say that the z component of E and B do not exist. So in other words, as we discussed previously, each del bar gives I times k, and dou by dou t is actually minus I times omega. So we substitute here in this. So this becomes k dot E, which is equal to 0, and k dot B, which is equal to 0. So when this dot product is 0, So we say that K is perpendicular to E and K is perpendicular to B. Therefore, the given wave vector K is perpendicular to E, B also. So we say that for using these two Maxwell's equations, we can say that the electromagnetic wave is a transverse wave. Now, the Faraday's imposed or Faraday's established a relation between field, electric and magnetic fields. So, by using this, we can establish a relation between electric field amplitudes, magnetic field amplitudes and wave vector. So, del cross E is equal to minus dou B by dou T. This is a Faraday's law. Now, we know from previous slide that the Z component of B is 0 and Z component of E is also 0, and the only components available here in this case X and Y components. As I said, the wave equation supports the plane waves, propagation of plane waves, or the solution of wave equation is actually a traveling wave or a plane wave. Now, we use this relation between E and B and try to establish the relation between amplitude and wave propagation. Now, where del cross E is actually, we can write I cap, J cap, K cap, dou by dou X, dou by dou Y, dou by dou Z. What is the E? E is the complex electric field amplitude e power kz minus omega t, and similarly this is E0x. Now we have E0y I kz minus omega t. What is K component, which is 0? Okay, minus dou by dou T B0x e power I kz minus omega t I cap plus B0y exponential of kz minus omega t j cap. So, what we do, we compare ith component and jth component. So, first ith component, dou by dou y of 0 minus dou by dou z of E0y exponential of I kz minus omega t, which is equal to minus dou by dou t of B0x times e power I kz minus omega t. So, the complex amplitudes are constants E0y, and the differentiation, what do we get? We get e power I exponential of I kz minus omega t, and similarly we get minus B0x minus I omega exponential of I kz minus omega t. So, this I will get cancelled and exponential terms also. So, we get E0y times K, this is K times of this is equal to minus into minus, minus into minus plus, and then so we have okay minus sign and then minus, there is also okay minus into minus plus. So, let us see this is plus B0x and omega. Okay, so let me check here, because we have there is a minus sign here. Okay, I forgot to put this. So this is the x component, and similarly we compare the y component. So we get for y component k times E0 x is equal to omega times B0 y. Now we combine these two equations. How? So when we combine in a more compact way, what do we get? B0 is equal to k cross E0 by omega. Now we can check this whether this is consistent or not. Now in this case we assume that the wave is propagating along z, so k times this and E0 by omega. Okay, suppose that we are looking at only the direction of propagation, or knowing the direction of wave propagation and the direction of electric field, we can fix the direction of a magnetic field. So this is a relation between electric and magnetic fields. For a monochromatic waves, and so here E and B are in phase and mutually perpendicular. E and B are in phase and mutually perpendicular. Okay. Now the real amplitudes are related by, so what is the magnitude, real amplitude of this B0, and k by omega, what is the magnitude of Z1? So this is E0, and we know what is k by omega, which is 1 by c. So this is a relation between electric field amplitude and magnetic field amplitudes. So now we can also write the using del cross B. Del cross B is equal to mu naught epsilon times dou E by dou T. We know that each wherever del is there, we can replace it by I dot k cross B bar is equal to mu naught epsilon times. So what do we get here? We get minus I omega times E bar. Okay, so simply, so E bar is equal to, we can write minus k bar cross B bar by mu naught epsilon times omega. Suppose wave direction is given to you and the direction of magnetic field is also given to you. You can fix the direction of magnetic electric field. So this is applicable only for plane waves, and similarly this is also applicable for plane waves. Remember this is very important. Now we look at 1-2 problems and then So the electric field of an electromagnetic wave a EM wave is given by okay, so E bar is equal to E0 cos of pi times 0.3x plus 0.4y minus 100,000 T into K cap. Okay, so this bracket here, there is no bracket here. So what's the question? Question is the associated magnetic field is the associated magnetic field is dash. So what do we do? First of all, we compare this with the solution. E is equal to E0 okay, cos of K dot R minus omega t. Now what is K? K is simply, we know R bar is x I cap plus y j cap plus z k cap. So what should be the K? So that K dot R is pi times 0.3x plus 0.4y. So this we can simply write, this implies K bar is equal to pi times 0.3 I cap 0.4 j cap. Okay, now what is omega? Omega is 1000 pi. What is a question? Question is we need to find out what is B. B bar is equal to K cross E bar by omega. Now we know what is K cross, and we also know the direction of E. E is along K cap. Okay, so we substitute this. So K bar is simply pi times 0.3 I cap plus 0.4 j cap cross E naught cos of this value, let's call this some theta, cos theta into K cap by omega, so that we get B bar. So when we do this cross product, when we do this, so we get B bar is equal to 10 power minus 3 minus 0.3 j cap plus 0.4 I cap E0 cos pi times 0.3 x plus 0.4 y minus 1000 t. Okay, this is the magnetic field that we get. One more question we do and then we stop here. Suppose the electric field of a an electromagnetic wave is given by E bar is equal to 2k cap minus 3j cap 10 power minus 3 sine of 10 to the power of 7 x plus 2y plus 3z minus beta t. The value of beta is c is the speed of a light. Okay, so what is the question? We need to find out value of beta. So what we do, we compare with our electric field. So this is in the form of sine of k dot r minus omega t. Okay, now what is k? Where k bar is 10 to the power of 7 I cap plus 2j cap plus 3k cap, and what is the magnitude of k, which is 10 power 7 under root of 1 plus 4 plus 9. So this is root 14 times 10 power 7, so meter inverse. Now what is the speed of the wave? We know speed of the wave is equal to v is equal to omega by k, where omega is 10 power 7 times beta by k value. K is 10 power 7 times root 14. So we get v is equal to beta by root 14. Now as it is moving in a free space, so v is equal to c, let's suppose. So beta is equal to c times root 14. Okay, now the last question we do. Suppose electric field is E is equal to z0 cos of root 3 by 2 k y plus 1 by 2 k z minus omega t x cap. Now we need to find out the direction of wave propagation. So we now compare this with our cos k dot r minus omega t. So this implies k dot is equal to root 3 by 2 k j cap plus 1 by 2 k cap. So this is the direction of wave propagation. Okay, so now we stop our lecture here. So thank you.